Alright, a little later than I was hoping to get this video made. However, I kind of had to build the smartboard, and that took a number of hours that I wasn't planning on putting into it, so it is the way it is. But this is your packet that you're getting on that last Friday before we all got locked up in our homes. And typically it's the last review packet we do. We do the data packet that we did do before break, and then we come back and we do the big algebra monster packet that has a lot of linear equation stuff, etc. And then finally we finished with a week on nonlinear functions, primarily for Algebra 1 level stuff, quadratic equations. So I'm gonna bust you through this. I have no idea how long it's going to take, because usually we do, a little bit of review each day. I'm going to try to do this all in one video. So if you don't need certain parts of this, you know what to do. Grab that little scrub button at the bottom and drag that thing across until you find what you're looking for. Let's review polynomials. That was more of a siren, wasn't it? That's as good as I can do. All right, here we go. So polynomials. Poly meaning many. Nomials are like names, terms from the Latin. And so we have a many-termed mathematical creatures. Now the terms, though, just can't be any math things. They do have to be contain variables being raised to integer exponents, basically. Okay, so the three parts of a term are your coefficient, which is a constant out front that tells you basically how many of those things you have as the variable. For us in algebra, it's usually an x, and then the exponent, which is the power of that particular term. You could have a single term. You could have many terms, but those are kind of the rules. Now, some people are like, well, what about a constant? What if it was just like a 5? Then it doesn't have a variable, so it can't be a term. But remember this little fact right here. X to the 0, anything raised to the 0 is actually 1. And so even if you do have a constant, it would be like it had an x to the 0 power. Okay. Now we have two primary ways that we classify polynomials: by the number of terms, or by the power of the function, the degree of the polynomial. So the three main terms that we use kind of through Algebra 2 for the number of terms are monomial or monomial for one term, depending on how you want to stress those syllables. So, like we just talked about, 5 only has one term. There's no variable, but it'd be like 5x to the 0. X, so it'd be like x to the first, 6w squared, etc. Those are all one-term creatures. Then we move to the two-term creatures, right? 5x and 7, two terms. Terms are separated by addition and subtraction signs. Okay, these are all two-term creatures. We call those binomials. We know bi means 2. And then finally, tri means 3. So trinomials have 3 terms: 1, 2, 3. 1, 2, 3. 1, 2, 3. And so that's how you classify them, by number of terms. Now, by the degree, if it's a first degree term, that means that the largest exponent in the entire equation is 1, which means you don't really see it, because when we have something to the first power, we don't write the first power, right? We don't see it. It's just understood. Kind of like we usually just write x. We don't write 1x. You could write a 1 in the exponent here, but we don't. But those are called linear. So those are going to create all the lines that we learned about in Algebra 1. If the polynomial has a degree of 2, so the largest exponent is a 2, we call that quadratic. And those are the ones I think more or less we're interested in right now, just because we're doing these circle problems, and a lot of you guys don't remember necessarily how to solve quadratics. And then cubics would have a 3rd degree. Luckily, you're not seeing very many of those. So this guy has top degree of 3. This is just a single cubic term. This one has 3 terms, but the biggest degree is 3 cubic. Now, it goes on. A 4th degree would be a quartic. A 5th degree would be a quintic, and so on. But, at a certain point, kind of like with polynomials, I think once we got past like a decagon with 12 sides, we were like, we're just going to call it a 13gon, a 14gon, a 15gon. And so at some point, we're just going to say, you know what, this is like the example there, 13th degree, polynomial. And that's kind of what you go with. All right, so we are now at the bottom of page 1 of your packet. These are just some examples. You can check really quick. How would you classify these? Well, this has 2 terms, so it's a binomial. It has a top degree of 1, so that would be a linear binomial, right? This guy right here has 3 terms, so that makes it a trinomial. Its top degree is 2, so it's a quadratic trinomial. And finally, this dude right here is just a single term, so a monomial with a degree of 3, so a cubic monomial. And that's how you do it. This is just some simple addition and subtraction of polynomials, a little bit of multiplication, which we typically call distribution. When you add to polynomials, a lot of times you don't even see the parentheses because addition is just do it from the left to the right. You don't really have to distribute a plus sign. So you would, 2x cubed plus 4x cubed would be 6x cubed, right? 7x squared minus plus a negative, so minus 6x squared would only be 1x squared. Notice there's only one x in here. There's not an x over here, so it would just be 1x plus 1x, and then minus the 12 is the only constant. So that's exactly what you would get. Boom. Okay. Now subtraction is an issue. Even like in my math and algebra classes, I often on problems that have subtracting binomials, issues with people forgetting to distribute that. And I tell you what, if you forget parentheses, which there's always 2 or 3 people per class who really struggle with parentheses. If you forget parentheses, you're just never going to remember it, because I'm not just subtracting 8x cubed here. I'm also subtracting 4x squared. I'm also subtracting a negative 5. Okay, all of that stuff is getting subtracted. And so 5x cubed minus 8x cubed is what, negative 3x cubed, okay? And then 6x squared minus 4x squared is what, 2x squared? And then there's only one x term, it's a negative 3x. And then look at that last 5. I'm actually subtracting a negative 5. We know that when we get a double negative, it turns into a positive. So not like it's a lot harder than the one above it, but you have to be more careful. Distribution, here I'm just distributing a single term. So don't just multiply the coefficients, also multiply the variables. When you multiply common variables, you add the powers. We don't have time to review exponent rules right now. It's a big thing in Algebra 2 also, because you'll study logarithms and you'll have to know all those exponent rules really well to understand logarithms. But 2 times 3 is obviously 6, but x squared times x squared, you have to add the exponents, because 2x's times another 2x's, I'm really multiplying 4x's, right? So that would be 6x to the 4th minus, what, 16x to the 3rd power, 16x cubed, and then plus 22x squared. So there you go. And then when I multiply binomials times binomials, boy, you got to get those parentheses in there. Otherwise, you're not distributing everything in the first by everything in the second. But what we do is we call a FOIL. We multiply the first terms, right? We multiply the outer terms, so that would be the x and the negative 3. We multiply the inner terms, that would be the 4 and the x. And finally, the last terms. And then simplify the middle terms. We'll usually simplify for you. And there you go. FOIL is not magic. It's just when you multiply a binomial times a binomial, you end up with 4 terms. And FOIL has 4 letters that describe the types of numbers that we're multiplying. So that's what FOIL is. It's just a tool to use to remember the parts. Okay. Now, as much as some people like FOIL, right? The box method that you probably were taught in Algebra 1 is more versatile, because FOIL only has 4 letters and it will only work for a binomial times a binomial. The box method also works for binomials times binomials. So watch this. X times x, right, when I fill this in, is going to be x squared, just like the first FOIL, right? And then when I do the outers, so that would be x times negative 3. Well, x times negative 3 right here, I get negative 3x. See, look, I'm getting all the same pieces that I got with FOIL. And so that's another way of doing the same problem. But how would I do look at this guy, a binomial times a trinomial? What? This guy has 2 terms, right? This guy has 3 terms. So this guy has to multiply by 3. This guy has to multiply by 3. What's 2 times 3? Of course it's 6. FOIL doesn't have 6 letters. And so in this case, you really do want to use the box method. If you need that tool to keep track of the pieces, once you get far enough along in math, you'll start finding other ways to make sure that you're not leaving any parts out. But look how quickly this would go. X times x squared, x times negative 4x, x times 7, and then of course the bottom row, you get those values, and then you just go through and you piece things together. Usually these diagonals will be able to be combined, and so you end up not with 6 terms in your final polynomial, but with 4. So this would be what, x cubed minus x squared minus 5x plus 21. That's what you would get. I don't know if I wrote the answer for you anywhere. It looks like I didn't, but that was it. I just said it. All right, so we are now moving on to the second page of that packet, or the back of the first page. Very, very important, factoring. Factoring is such an important concept and tool that's used all the time that we sacrifice a full day of factoring and trigonometry, even though students have already learned it all by that point, just to review it. And the very next semester, not even a year later, the very next semester, we spend another full day reviewing factoring and math analysis. There's 5 primary factoring methods, and you should learn probably 3 of them in Algebra 1 and then get the other 2 tacked on in Algebra 2. So a couple of these you're really not required to have down yet, but I definitely want you to know the first 3. In simplest terms, factoring is just breaking a number up using division into its multiples. With, in elementary school, you did this with numbers. You're like, hey, factor 10. And you're like, 2 times 5. And the teacher was like, good job, go to recess. Don't you miss recess? And sometimes you could do prime factorizations and break things up even more, right? So 20 could be 2 times 10, but 10 could be 2 times 5. So we got 2 times 2 times 5. That was called a prime factorization. Some polynomials we're going to find can actually be factored multiple ways. You can use one method and then follow it up with another method. It doesn't happen super often, but it's something you definitely want to keep your eye out for. So as I mentioned, 5 major factoring methods. The most common one, the first one you ever learn in Algebra 1, is factoring out a common term, or factoring out a monomial, okay? That's where you look at your terms. In this case, I just have 2, 12x squared, and 18x, and I'm like, what do they have in common? Well, 12 and 18 have a 6, x squared and x have an x. You can only take as many x's or variables as the least one is. And so you factor those out, which means divide them out, right? And so that's how you factor a common term. You just look and see what factors the coefficients have in common, and then what variables the terms have in common. Factoring difference of squares, probably the next one you learn. It, to me, is one of the easiest ones because it's a very, very recognizable pattern. It is a difference, so that means subtraction, right, of 2 perfect squares. So this has to be a perfect square, and this has to be a perfect square. It can't be a sum of perfect squares. It can only be a difference of perfect squares. And it always factors the same way. It factors into these two binomials we call conjugates, because they're identical, except for one of them is a difference of the terms and one of them is a sum of the same 2 terms. And so we'll take a look at a couple of those for you here in a second. Factoring trinomials into binomials is probably the one that's the most difficult for a lot of people um, in Algebra 1. It's it just takes a lot of practice, and we'll do some today, and I'll try to give you some ideas about how to do that in this video. So if that's really all you need, you can certainly scrub ahead and get to that point. But you end up with a trinomial. It's almost, for at this level, it's almost always going to be quadratic, second degree, and we just need to, you know, basically start with two parentheses and fill each parenthesis with a binomial. And yeah, we'll talk about that in just a second. Now, the ones that you're going to eventually see next year are factoring sum and difference of not squares but cubes this time. So these are just formulas that you have to memorize, and once you kind of realize how similar they are and how it works, they're not that bad. For example, a cube plus b cubed, the first binomial is just a plus b. So you just take the first thing times the second thing without the cube. Now, the trinomial is the first term of the binomial squared, so a gets squared, and then this sign right here, okay, is always going to be the opposite of this sign, and that's the one thing you got to remember, okay? And once you subtract, it's just the two things multiplied by each other, a times b. And then the last term is always positive, and it's always the second term squared. It's always the second term squared. So it's just a pattern. You can see that with the difference of cubes, it's the same, except I start with a minus b. And then that means that the second term here is a plus instead of minus. Factoring by grouping, actually, some people are taught this in Algebra 1, not for use with four-term expressions like the one I have here, but indeed with trinomials. And they break the trinomials up to find common factors with the first two parts and the second two parts. You basically take the middle term and do it. I never really taught it that way in Algebra 1, but some teachers kind of like it, and some students actually find it helpful. Now, this is a different kind of factoring by grouping, and it works where there's nothing that goes into all you really know you need to use this when you have 4 terms or 6 terms or 8 or 9 terms, you know, way more than 3 terms basically. But you basically don't have anything that goes into everything. Like 2 and 3 go into 6, but 2 doesn't go into 15, and 3 doesn't go into 8, and most of them have x's, but 20 doesn't have an x, and so there's nothing I can take out from everything. So you just kind of isolate 2 at a time. With the 6x cubed and the 15x squared, I could definitely take out a 3, and I can take out 2 x's, x squared. That leaves me with 2x minus 5 left over, okay? Now with the 8x and the 20, the only thing they really have in common is a 4, leaving me with a 2x here minus a 5 here. Now, here's why this actually ends up working. We started this process with 1, 2, 3, 4 terms. That's an awful lot. Now I only have 1, 2 terms. See how the plus is just between the two pieces? And it's a lot easier to find something in common if you only have 2 terms instead of 5 terms. And if you look really closely, you can see that the common term isn't just a single thing, it's a binomial. The 2x minus 5 is common amongst these two things. So what would, if I factor that out, what would be left over here? Well, just the 3x squared. Plus what? What would be left over here if I took out the 2x minus 5, just the 4? And there you go. Fancy, huh? So that's a little sneak peek of factoring by grouping, something you may see next year, especially if you never saw that in Algebra 1. You definitely don't really need it right now for our purposes. I almost said porpoises. That would have been weird because there's not even an ocean bordering Colorado. All right, so these are just the practice problems, and I'm just gonna bust through here, and you can look at them again and again if you need to. But you know what comes out of a A 12 and a 21, probably a 3. What comes out of an x squared and an x? Probably an x, right? Now, remember, those aren't being subtracted out, they're being divided out. So this would be a 4x left over, and this would be a 7, just a 7 left over. The great thing about factoring is you can always test your accuracy, because if you redistribute, you don't even have to do it on paper, you just do it in your head. You have to end up with what you started with, okay? And yeah, that's it. Pretty easy, huh? What about here? Well, the 27, the 45, and the 18 actually all have 9 in common. And the x to the fourth, x cubed, and x squared all have at least 2 x's, right? I don't really mean 2 x's, I guess I mean x squared. But now we need to divide those out. So dividing the 9 out would leave me a 3, a 5, and a 2, I guess technically a negative 5, and then dividing the x squared out, I'm subtracting the exponents when I divide exponents. So I'd have x squared, x, and then 2. The x squared totally cancels, so just 2. So there you go. There's your answer. Factoring out a monomial. I told you perfect squares is easy. It really is. Here's where I have those things called conjugates. Right? These are, I have it here in your notes here, conjugates. And they're binomials that are the same, except one of them's a difference, one of them's a sum. And you can see if I FOILed it, these are the pieces I would get right here, right? But notice that these middle terms always go away. That's the power of conjugates. That's the beauty, and that's why you get such a simple thing called difference of squares when it's all said and done, okay? So you just basically say, what's the square root of the first thing? X. What's the square root of the second thing? 5. One of them's plus, one of them's minus, done. What's the square root of 81x squared? Well, 81's a perfect square, x squared's a perfect square, so 9x, right? What's the square root of 49? 7. Man, difference of squares, I wish they were all that easy. So that leads us to the trinomial factoring, which I think is probably the thing that would help you the most to practice leading into this, this last part of this chapter with some of these circle problems. It only took us, it looks like 22 minutes to get to this part, but hopefully it pays off for you, okay? Here's the idea, okay? If you really want to know how to factor, you have to be really good at thinking backwards. Okay, if you have a quadratic trinomial and you want to factor into 2 binomials, you really want to know how to play the game of numbers. The game of finding numbers. What game is that? I'm going to teach you, okay? Because when you start thinking backwards, and boy, I tell you, Algebra 1 and Algebra 2 teachers have all kinds of fancy little like crisscrosses and ways of setting this up, but none of that's really going to help you a ton if you don't understand why you're doing it. Here's what it breaks down into. If I was going to distribute 2 binomials, FOIL them out, this first term right here, this x squared, right, is always going to come from multiplying the first 2 terms, the firsts, right? And if it's an x squared, like a lot of your problems will be, that makes it super easy, super easy. It's just going to be x times x. Okay, so the first 2 terms are always going to create that that first term up there. Now, there's always going to be hints you can get from the binomial, and the easiest one, I think, is looking at, is the last term positive or negative? If it's positive, you can only get positives by multiplying positives by positives or negatives times negatives. If it's negative, like this case, you have to have one of each. And so that's a huge hint. You know that one of these has to be a plus and one of these has to be a minus, right? This is where the game of numbers comes in. Multiplying these 2 lasts, right? We already did the firsts. We got that out of the way. That was the x squared. The lasts is always going to give you this 14. We don't know what those are right now. Those are unknown. But when I multiply those 2 values together, that's always going to give me that last term. So you're always looking for 2 numbers that multiply to equal the last part of the trinomial. And yet when you do the OI of FOIL, right, the O and the I, which would be the outers and the inners, which would be these 2 dudes and these 2 dudes, and you put those together, they have to equal the middle term. So they're multiplying to equal negative 14, but they're adding to equal -5. Some of you guys I know are like yelling at me right now. I know what it is. It's -7 and +2. Um, you got it right. But some people have a hard time seeing those just as well. Okay, what numbers are going to multiply to this, but add to this? And that's how you play the game of finding numbers, is by coming up with um, that. So let's play. Let's play a couple rounds. We are now, holy cow, we moved on through page 2. We're now on page 3 of your packet, and it looks like this, except a lot longer. Okay, the game of finding numbers. And look what it is. It's just practice making your mind think in terms of getting the right pair of numbers, sum to something and multiply to something. So what two numbers, and I usually start with the multiplying because that's a little easier. There's always going to be less factors than there are going to be less, numbers that add up to something. So what number is multiplied to -35? But when you add up to 2, +2, okay? Um, well, there aren't too many numbers that go in 35. I mean, 1 and 35. Probably the next one would be 5 and 7. Now, because it's a negative, I have to have a negative times positive. And so it's really adding two numbers together where I'm looking for the difference between them. And so is the difference between 5 and 7 2? Yes, it is. So now all we have to do is determine, should I have the bigger number be positive or negative? And because the sum is positive, the bigger number should be positive. So that's +7, -5. That's it. +7, -5. Okay. What two numbers multiply to 6? Well, there's only two possibilities. 1 and 6, 2 and 3. Um, they both have to be positive because they're multiplying to a positive and adding to a positive. And so is 1 plus 6 5, or is 2 plus 3 5? Yes, 2 plus 3, right? That's incorrect, isn't it? 1 plus 1 plus 6 is 7. So ignore that. That must have not got fixed from like earlier when I was flying through this. All right, 13 and um, 30. 13 and 30. So 30 is either 1 times 30, 2 times 15, 3 times 10, maybe 5 times 6. Which of those add up to 13? Once again, it has to be a positive times a positive because both terms are positive, right? And so if you said 10 times 3, hopefully we get it right this time. Yes, very good. Number 4, positive again. So is it 1 times 10 or 2 times 5? That's the only way to multiply to 10. Oh, yep, 2 times 5 adds up to 7, right? Now we start getting into some negatives. So I need a positive times a negative to equal -4. So is it 1 and 4 that have a difference of 3, or is it 2 and 2 that have a difference of 3? No, 2 and 2 have a difference of 0. That would be like difference of squares. So it's got to be a 4 and a 1, and because this is a -3, the bigger number has to be the negative. So -4, +1. Okay. Number 6, -20. So once again, I need a positive and a negative to multiply. So 1 and 20, 2 and 10, 4 and 5. Which of those have a difference? Since one of them is positive and one of them is negative, which one has a difference of 8? Yes, the difference between 2 and 10 is 8. Because 8 is positive, I need the bigger number, the 10, to be positive and the 2 to be negative. 14 is positive, but look, the sum is negative. So this is the first one we have where I'm going to have to multiply two negatives to create the positive, and yet they have to add up to -9. So is it 1 and 14 that add up to 9, or 2 and 7? Yes, so it's -2, -7, right? And that's how you play the game of numbers. You certainly do not have to do this. You certainly do not have to do this, okay? But what I'm going to do is let you pause the video, and I'm going to reveal these as we go. So if you pause it and try them and see if you want to do them, it's totally up to you. I know it doesn't take long, but here we go. I'm just going to bust these answers out and let you check if you want to. Okay, this is all totally optional. I can't even hit these in order, can I? There we go. All right, and then the last set over here. I have some starred ones. I'll save those for last because I do want to talk about those a little bit. They're special cases, is what those are. And so why is 8 and 16 special? Well, because to multiply to positive 16 and add to positive 8, I have to use a 4 and a 4, right? And so they're the same number. And so that is a square binomial. That's what that would end up being. Once we built it, it would be like x plus 4 times x plus 4, or x plus 4 quantity squared. It's very similar to number 23, except number 23 is a squared difference binomial. I need a negative 6 times a negative 6 to multiply to 36 but add to negative 12. So whenever you have the same factor on both of them, that's a special pattern, and it has some special features to it graphically too. So those are special patterns. And here is a page of notes a little further along, and I'll touch base on this when I get there, but don't worry about it right now. The only other one that was really special in here was 21. 21. Notice the sum is 0. Well, the only way you can add and get a 0 is if you're adding opposites. But look at the negative 9. The negative 9 is a perfect square. Not the negative part, but the 9 part. So how about 3 times negative 3, right? 3 times negative 3. Now think about that. X minus 3x plus 3. That would give us difference of squares. So these are perfect square binomials. 23 and 17, 21 is what we would call difference of squares. So moving on. So now that you've played the game of finding numbers, factoring binomials should start to get a little bit easier, okay? Because we're really just asking, we know that, we know we're going to start with x and x to get x squared, but what two numbers multiply to 12, add to 7? Boom, 3 and 4, right? What two numbers multiply to negative 18, so it's going to have to be a positive and a negative, right? But add to 7, so positive 9, negative 2, right? What two numbers multiply to negative 24? Oh, negative, so positive, negative, but add to negative 2. So how about negative 6, positive 4? That's not even close. That's the second error. I was working too fast today. This one should have been negative 6, positive 4 to make that one work. Okay. Let's do example D. Negative times a negative is going to add to a negative but multiply to a positive. And then how about 3 and 10? No. 5 and 6. 5 and 6, right? There you go. Now, these get a little more spicy, a little more interesting, because I have a lead coefficient. Okay, that's not a 1, but it's a prime number. There's only one way to multiply to get 3, and that's 3 times 1. So I'm going to do 3x times 1x. Okay. Also, because I'm multiplying to get a negative, I have a positive and a negative. I have to hold off a little bit. I have to hold off to see which one's positive, because whether the negative is with the 3x or x will make a difference. So now I'm just looking for, how do I multiply that 8? Is it 2 times 4? Is it 1 times 8? Some of these you may have to guess a couple. You won't have to guess too many. Once they start getting nasty and you have to guess a lot, then we get fancy algorithms working, things called the California method, all right? So I think that this one is going to be a minus 2 and a plus 4. Now, why do I say that? Well, obviously, when I multiply those, I get negative 8. But if I FOIL 3x times positive 4 is 12x, and negative 2 times x is negative 2x, and 12x minus 2x gives me that positive 10x. So the more of these you do, the better you get at them, okay? Now this one has an 8x out front, so that's like, oh no, now I have like, two different ways to get the x squared. But first of all, notice that the last term, which we don't even see yet, but it's positive, and the middle term's negative, so it's a negative times a negative. And the last term is a prime number, 5. So that's just as nice as the first term being a prime number. There's only one way to get a 5. So now we just have to figure out how to multiply to get that 8. And I'm thinking we're probably going to want to do a, boy, 22 is pretty big. So I'll take the bigger number, 4, and multiply that by the smaller number over here too. So that means that the 4 gets to multiply by the 5. So there's your negative 20x, and then here's your negative 2x, which goes together to make the negative 22x total. Okay, so this is the kind that you'll probably have to do on some of the problems on tomorrow's quiz, or I guess it's 12:05, so we can now say today's quiz. But they won't get any harder than these. So don't sweat it too much. Okay. Here are some that get a little spicier, but these aren't as bad if you consider combinations. So always look to factor out just a common term first if you can. That makes the rest of it so much easier. Okay. So for example, in example A here, 60 is a big number, and there's a lot of ways to multiply to get it. But if I factor a 2 out of every one of these, and I can, because they're all divisible by 2, now I just have an x squared and a 30, and there's less ways to multiply to get a 30. And they need to both be negative because the middle term is negative. So what factors of 30 add up to negative 13? How about negative 3 and negative 10? Okay, so by factoring out that common monomial first, it really helps. Same thing here. I can factor out a 5 first. If I don't have difference of squares. 45 is not a perfect square. 20 is not a perfect square. But look what happens when I factor out that 5. Oh, 9x squared is a perfect square. 3x, 4 is a perfect square. 2, 2. So I get those conjugates, right? 3x minus 2, 3x plus 2. So don't ever give up when you have a possible combination. All right. There are 2 more important ways that you'll learn to factor, but like I told you earlier, you don't really have to worry about them right now. So you can fast forward, or I'll spend a couple minutes talking about them really quick. We already talked about these patterns here. This is just a little mini proof that the patterns really work. Like I did the cube pattern, so that's difference of cubes right here, right? Will I really get a cubed minus b cubed? And the answer is yes, because a times a squared is a cubed. A times ab is a squared b. A times b squared is ab squared. See how I'm just filling in the boxes? A squared times negative b is going to be negative ab squared. AB times negative b is also going to be a negative, and it's going to be a b squared. And then finally, negative b times positive b squared is negative b cubed. Now I told you a little bit earlier that most of the time you're going to get these diagonals going together. Well, not only do they go together this time, but look, they're exact opposites. A squared b, negative a squared b. AB squared, negative AB squared. Those go away. All you have left is a squared, a cubed minus b cubed. And it looks like I have my third mistake here because I lost the negative sign here. I'm going to have to start making a list of all of these because there's starting to be too many. All right. Go back and fix them for future prosperity, right? So how would I do this then? Well, like I said, if it's a sum, the binomial is going to be a sum. you just take the cube root of each of these. The cube root of x cubed is x. 27 is 3 times 3 times 3. You should definitely know your first 10 perfect cubes. It'll help you out a lot. This first term, according to our formula, is the first term over here squared. So x squared is just x squared. The sign that you get here is always going to be the opposite of the sign I get here. Look at when I do the difference formula, the binomials of difference, the first sign here is the opposite. When I do the sum of cubes, the first thing's a sum, but the first one I come to in the trinomial is the opposite. So that's how you remember what that is. To get that middle term, you just multiply these two things together. X times 3 is 3x, right? And then the last term is always positive, and it's just the second term, and it is squared. So that's how easy it is to use these formulas, but you definitely don't need them for this class. You will learn them next year. Same thing with grouping. You know, we don't see anything in common with all of these pieces here, okay? But if I take those four terms and find those common factors, right, which in this case, 3a squared for the first two, 4 for the second two. This is the exact same one we did earlier. Look at that. I went from 4 terms to just 2 terms, and those 2 terms have that 2a minus 5 together, and there you go. So, you know, we started with 1, 2, 3, 4 terms. Now we just have 1, 2 terms. That makes things so much happier, so much easier. Once again, factoring by grouping, not super imperative right now. All right, these are the 3 special binomials that we talked about a little bit earlier. Difference of squares. This is the one. This guy loves difference of squares. Look at that. Holy cow. These are the ones that I always warn you about. A plus b squared is not, okay, it's not a squared plus b squared. A minus b squared is not a squared minus b squared. You can't just distribute the thing. Remember this girl? Stop trying to make a plus b squared, a squared plus b squared happen. Stop trying to make it happen. It's not going to happen. It's never going to happen. I do still have very common mistakes on that made in math analysis. You know, pre-calc, people are still doing that. But a plus b quantity squared means you have to multiply a plus b by a plus b. And so you get this very special formula where you get an a squared at the beginning, a b squared at the end, but you also get a couple ab's in the middle, right? Foil, outers, inners, the oi of foil gives you a couple of those ab's. And so it's a very famous formula. The reason that I bring these up right here and make such a big deal out of them, and you know, we're all the way at the bottom now of page 4, right? You see these listed. Is because the SAT and the PSAT tests love these things. Oh, they're always using these. They're always putting them here and there. You'll know these will pop up at least a couple times on every single test they ever give. So, so know these. They're in your packet. It's a good reference, and you can kind of practice them. You know, here's a difference of squares, right? So square root of this, one of them's minus, one of them's plus. I think those are usually the easiest ones. Here's that sum of not sum of cubes, the square binomial, square sum binomial. And so notice the relationship right here. This is a huge relationship you want to really focus in on, okay? What's the relationship between 8 and 16? This is something that you need to know when you do something called completing the square, which we have to do in geometry when we find standard equations of circles. We have to. You're going to be doing that way sooner than it sounds like you're going to be doing that. Okay, it's a fairly simple process, but it's mega important. Okay, and so you want to know that to get from 8 to 16, the 8 comes from adding 2 of these together. The 16 comes from multiplying 2 of these together. So to figure out what that number is, that 4 is, that I need to square to get to 16, I have to divide 8 by 2. And that's really the trick. 8 divided by 2 is 4, squared is 16. If you know how to do that, then you know how to do this thing called completing the square, which is going to be coming down the road. Okay. Um, Same thing here. Okay. X minus 7 squared is really x minus 7 times x minus 7. But look at the pattern. Half of 14 is 7. Squared is 49. See how beautiful that is? And by the way, negative 7 times negative 7 still makes a positive 49, doesn't it? Negative times a negative. Here's just a proof of the x plus y formula. X times x times y is the outers. Another x times y for the inners. Okay, and then finally at the end, the y times y. And the two xy's go together. Okay? Don't make this mistake right here. Don't do it. It's too sad. Too sad. Oh, makes me want to cry right now. All right, this is another, we're now on page 5, I think. It's another game of finding numbers. I will put all these answers up here for you, and then you can either pause and play the game of numbers, or you can just unpause and we'll move on. But this is just a resource for you to check at your own leisure if you want to do the game. This right here looks like me teaching you how to do the California method. That's a weird place to put that, but that's what that is. I'll tell you what, I'll come back to this at the very end of this video and teach you this algorithm called the California method, which allows you to factor kind of nasty, um, trinomials. Okay. All right. We go to page 5. All we're going to do on page 5 is practice factoring. And it kind of has a sequence, so you're doing a common term, and then you're doing trinomials and the binomials, and then you're doing perfect squares, and so on. So I'm not going to do these, but any of these you want to do for practice, I'm going to show you all the answers so that you have the ability to come back and check, and then use this video to check your work. Notice like 22 and 23 are special because they can be factored twice. Factor out a common term, then factor difference of squares. Number 24 couldn't be factored because it looked like it was difference of squares, but it was sum of squares, which doesn't work. Haha. Most of these answers are probably right, but I've already gotten 3 of them wrong. So if there's a problem, maybe there really is a problem. All right, that brings us to page 7. Okay, keep using that pause button if there's any of these that you want to practice before you see the answers. These are the first half of the answers on page 7. Okay, the first half of the answers. Right? And then here are the second half of the answers on page 7. So ton of factoring practice at your disposal. Ton. But we really want to get to page 8. Page 8 is such an important page. This is the beginning of Quadratica, where we learn to solve quadratic equations. Although you already learned how to do it in Algebra 1, we're really just reviewing it. So let us move into that wonderful land of Quadratica. All right. These are the 4 primary forms that you'll see quadratic equations in. I guess there's one more that I can show you at the bottom, but here's what we got. This is the one that you really should know by heart. This is the one that is the one you're going to see the most often, and it's just called standard form ax squared plus bx plus c. We see the x squared in there, and this will always allow you to attempt to factor a quadratic. This will, if you set it equal to 0, that is, this will always allow you, if it's set equal to 0, to use the infamous quadratic formula. So that's right here. Know this guy inside out, right? This is such an important formula. The vertex form is something you play around with a lot in Algebra 2, but I do know that you play with vertex form a little bit in Algebra 1. Vertex form of quadratics and I think absolute value functions. HK tells you where the vertex is, A is either positive or negative, right? It's either going up or down, and that's really what it is. Now I'm putting a bunch of extra cool stuff in here that you can read about, but we don't have time to get into the nitty gritty. Like, how do I know that h is negative b over 2a? And how do I know that k is just, f of h? Fun things, but we don't have time to get into it. Intercept form is the kind where you're going to try to factor it. So that's actually a really good form to look at. But P and Q in that form tell you where it crosses the x-axis. So this is a good graphing form. And in Algebra 2, you'll use your graphing calculators a ton to solve quadratic formulas and other polynomial formulas. Conic form is something you won't learn about until math analysis, pre-calc, and it is another way of writing a parabola. But this is the general form of a parabola. And things just get spicier because, like, if there's no cy squared term, right, and everything else is there, then what you get is you get a parabola. Or if there's no ax squared term and you just have a cy squared term, and then you get a parabola. Here's where things get dicey. If there's just a cy squared term, it's not the parabola that we get from all these equations. It becomes what's called a horizontal parabola. So if you have a y squared and not an x squared, you get one of these. You don't study these in algebra because it's not even a function. This is a relationship that's not a function because it doesn't pass the vertical line test, right? And then if there is this term right here, see this bxy? That is a funky dude. We usually don't even have time to mess with that in math analysis. But what that does is that starts rotating. Remember when we did all of the transformations of shapes last fall with the triangles and stuff, and we did dilations and transformation or translations, reflections. Well, you could use that dxy term, and you could turn um, your parabola any 360 degrees, anywhere around the the entire coordinate plane. You can make it rotate. So it gets into some really funky stuff you don't need to worry about right now. But what you really do need to know is ax squared plus bx plus c, because then you can use the quadratic formula anytime you want. Here's some important ideas about parabolas. Quadratic equations always produce parabolas. There's no ends, ifs, and buts about it. The point at the lowest point, or possibly the highest point, if it's been reflected and is opening downward, is called the vertex. So that's a very important term. It's called the vertex, right? Parabolas cross the x-axis at these things called roots or zeros, because on the x-axis the y value is 0. They can be either 2, 1, or no real roots for a parabola. This one actually is one of the examples that has exactly 1. It just hits it once. And then the quadratic formula, that's our buddy right there, right? The quadratic formula can be used to solve every single quadratic that ever existed. Even if there aren't any real roots, there's only these things called imaginary roots you'll learn about in Algebra 2. You can still use it. Now this one, like we said, has exactly 1 root, so it's actually called a double root. Speaking of numbers of roots, let's talk about the discriminant. So we're still on page 8. This is at the bottom. The discriminant, which sounds like a kind of gnarly thing, is really just the part of the root inside. And so if you just plug a, b, and c in here and test it, it's either going to be positive, right? It's either going to be positive, or it's going to be negative, or maybe, if you're really lucky, it'll be exactly 0. Okay, so how does that impact what we're talking about here? Well, if it's positive, that means you're going to get a value that you're going to have to add and subtract as part of this formula. And so it's telling you have 2 different answers because it crosses the x-axis 2 different times. If it's negative, it tells you you get a negative number in a root. And negative square roots are impossible. So even if you took a perfect square like 9 and made it negative, the only way to multiply to get a negative 9 would be a positive 3 times a negative 3. Well, those aren't the same, so they're not really perfect squares, right? And when you get a negative inside of here, you get imaginary roots that don't show up as real roots. So that means it doesn't cross the x-axis ever. Finally, the special case where the discriminant is exactly zero. Well, if this zeroes out in here, it doesn't matter whether you add or subtract the square root of zero, it's just zero. So then really all you have left is this part of the equation, and you just have one answer. That's why, remember way back on the front page, or I guess not the front page, but up above on page 8 here, for vertex form, it tells you that h is equal to negative b over 2a. Um, this is kind of where that concept comes from right here. Okay. And you can see a very similar picture to the last page where we just hit the x-axis once. So you don't cross it, you just kiss off it. We're studying tangent lines, right? Well, this, you could say that the x-axis is tangent to the parabola. It only hits it once, okay? And in Algebra 2, you'll learn that's called a double root, and that's kind of a special case, but that's what that is. So moving on, we go to page 9, which is actually not a list of information about parabolas, but this page of notes tells you how to solve them. Method 1 is your favorite method, but it only works if there's no bx term, because then you can just solve. Look how I just solve for x squared and take the square root. The only thing people forget is there's two answers, right? A positive root and a negative root. Other than that, that's the easiest method because there's no bx term. Unfortunately, usually that's not the case, okay? And so then this is the method that I'm totally trying to get you guys to use. This is called the factory method. So first thing, you'll see this on almost all of these methods from now on out. Set it equal to zero. You gotta set it equal to zero, okay? Once you set it equal to zero, you can see if you can solve what remains there. And then each one of those, see, now we're using what's called the zero property, okay? The zero property says if you multiply x times y and the answer is zero, the only way you can do that is if one of those numbers or both of those numbers are zero. You can't get zero through multiplication unless you're multiplying by zero. And so when I set these two factors, each equal to zero, right? It's pretty easy to figure out what those are. And you guys have been doing these types of problems over the last couple nights. This is just really verifying that you understand that concept. All right. So this is where you really stuck and you can't factor it. What are we going to do? We're going to call upon the good old quadratic formula. So notice that the first thing you do still is set it equal to zero. Set it equal to zero. Once it's set equal to zero, you can determine um, what the A is always with the x squared, the B is always with the x. Don't forget the sign, so this is actually negative 7, and the C is negative 4. And then we plug in. So look at how I plug B and A and C in. Follow order of operations. Double negative 7 is 7. Negative 7 squared is a positive 49, negative times a negative. Here I get negative 4 times 2 times negative 4. So once again, a negative times a negative actually makes that positive. This one works out wonderfully because 81 is a perfect square. It's 9, right? So now I'm either adding or subtracting 9, and this is where you have to break it into two cases. This was by the way the exact same problem we just did in example 2 or method 2, and look, I got the same answers. Okay. A lot more work though. If you can factor it, it's way easier. This is something I want you to understand about the quadratic formula. Okay. This is the exact list of reference information that every PSAT 9, PSAT 10, or even SAT exam gives you. It has not changed in decades. What do you notice about every one of these formulas? They're all geometric. They're all geometric. Every single one of these formulas is geometry. And yet even the SAT only has about 6 or 7 geometry questions on it. The PSAT 9 doesn't have any. They still give it to you, even though there's no geometry problems. Isn't that a sick joke? So what I'm trying to establish here is that this quadratic formula will not be given to you. It's something you really have to work to memorize. It's important. It's one of the pinnacle things you learn in Algebra 1. And there's even a cool song that goes with it. And it goes like this. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So sorry you had to listen to that, but know it, don't forget it. I'm not going to get into the graphing method too much because we'll really study it next semester, or next year I should say, a lot, but you still set it equal to 0 first, because 0 is going to, when y is 0 is going to indicate where the roots of your function are. The great thing about doing these on the calculator is you can use calculator operations and it'll just tell you what the roots are. Okay, look at how it found it for me. Okay, I can hear some of you guys like wanting to see this already. All right, here we go. I'll just make one up. Okay, this one won't even probably have rational roots, so this one's a good one. So we'll do 3x squared, I don't know, plus 7x minus 11. I made a really nasty one just to try to make one that for sure doesn't, isn't factorable. Okay, so here we go. Look at that. Yeah, definitely some weird looking answers, right? But you can see right in here and here is where they are. So here's how how quickly the calculator can find those. You go to the menu, you tell it you want to analyze this graph, and you want to find a 0. It asks for what's called a lower bound, so you go a little bit to one side of the answer and hit enter. It says give you an upper bound, so you go over it, and as soon as I go across that root, it gives me the answer right away. Boom. So notice the y value is 0 because we're on the x-axis, but that first part is your answer. Negative 1.08 is the approximate value. Most of these are irrational answers, so it's an approximation. So there you go. A little glimpse at next year. Completing the square is an interesting method because it works every single time, but it's not used a whole lot in our level of mathematics. What you're trying to do is use our little formulas for perfect squares and understanding that relationship. Do you remember what it was when we talked about the relationship between 2y and y squared, basically, um, between 9 and 6? Oh yeah, I take half of 6, which is 3, and then square it to get 9. Okay, and so I'll just let you look at this example, but you certainly don't have to understand it. What if I had this right here and I wanted to complete the square? The first thing I'll do is move all the x's to one side and all the non-x's to the other side. So I'm going to subtract 3x over and add 32 over, and this is what I get. Okay, so now I do that little trick. I look at the middle term, which is 2x, and I'm like, all right, if I take half of that, I get 1, but then I have to square it. Well, 1 squared is just 1. So if I add 1 over here, I'm going to create this beautiful pattern right here. Okay, but the one thing I have to remember is I can't just add 1 to one side. I have to also add it to the other side. So I add 1 to both sides. Now this becomes x plus 1 times x plus 1 when I like reverse FOIL it. Okay, and x plus 1 times x plus 1 is just x plus 1 squared. Now here's how you use this method to solve. The opposite of squaring is square rooting, so I take the square root of both sides. Be careful that you don't forget that 25 square rooted is plus or minus 5. And now I just have to subtract 1 from positive 5 and subtract 1 from negative 5 to solve the two answers. So that's the method called completing the square. There's a lot of information out there. I just sat on Google Images for about 2 minutes and found just a ton of, this one has all the different forms we were just talking about. It's just a different way of looking at it. This one talks about different methods of solving and has some diagrams. Some of them are better than others, but there's so much of this stuff out there. Here's that crazy completing the square method that I just took you through. If you want another example of that. Don't be shy. There's a lot of information. So I think that's about it. I think we're good for this little review. I know it was a long one, but we just went through a ton of pages. This particular um, page 10, just has some practice problems solving the different factoring method. It looks like at the top, solving algebraically here. So I think that means probably there's no bx term, so you can just shortcut it. I don't know why so much of this page is empty. It's kind of weird. I don't know what's going on there. Here's some graphs. Oh no, okay. So I had an extra page in mine that shouldn't be in yours. Page 10. Huh. All right. Well, anyway, um, here you can just look at the graphs and estimate the answers. Notice this one only has one, so that's a single root problem. This one has 0 real answers, right? So you play around with the rest of these as much as you want. I don't have any answers for these 18 problems, but I think I had some more. Here we go. Once you get to the 4 methods, 4 ways page, here's some answers for 1 through 3. For those of you that really feel like you need extra practice, 4 through 6. Okay, 7 through 10. These are estimate answers here, right? We can't tell exactly what the answers are. Those are estimations. Number 11 was supposed to be done in a graphing calculator, so obviously some of you guys don't have these graphing calculators, but that's okay. You don't have to do it for this class anyway. This is just a quick chance for you to check some answers if you want to. And quadratic formula, doing one of these wouldn't hurt you because the quadratic formula does take a lot of practice. There's a lot of algebra going on. Very powerful formula, but not my favorite to use. It just takes so much simplification to go through it. Here's a couple more of those. Okay. What's this at the bottom? 10 is algebra 2, where the numbers are imaginary. Just like my friends. Oh, that's pretty funny. All right. Here's another one. And here's where we just used the discriminant to determine how many answers there were. So we're just doing the b squared minus 4ac. And I think that's the end of the packet. What if algebra teachers are pirates and they just want you to find X so they can steal your treasure? All right. So I did promise I'd go back and show the California method. So if any of you were sticking around through this tremendously long thing, holy cow, I can't believe I'm still up. I will show you how to do it right now. The rest of you hopefully are tuned out and getting ready to take the quiz. Gotta remember where I put it. It wasn't here, was it? No. I think it might have been on one of these pages. I'll find it for you here pretty soon. There it is. It was on this one. Okay. So this is a method called the California method. And if you look at this trinomial I have sitting there for you, 12x squared plus 44x minus 45, here's what makes this kind of nasty, okay? First of all, there's 3 different ways to get a 12. So I could get that first term by doing, x times 12x, 2x times 6x, or 3x times 4x. I also have a number of ways to get a 45. 1 times 45, 3 times 15, 5 times 9, right? So there's 3 ways to get the first part. There's 3 ways to get the last part. 3 times 3 is already presenting me with a total of 9 ways. But then I could switch the last two terms and double that up to 18 different possibilities. And technically there's really 36 because you could switch to positive and negative signs. But really, 18 possibilities. That's probably to a point where I don't want to guess and check anymore. Okay, so this is there's many different people do the California method many different ways. You may learn it a different way in Algebra 2, but I will show you the way I do it right now. I start by taking the lead coefficient, which is 12, and putting it into my binomials, and I put 12 into both of them. I know that's really weird because 12 times 12 is not equal to 12, but we fixed that at the end, so don't worry about that yet. Okay. Now, here's where the California method's algorithm starts. You take the first term, the A, and multiply it by the last term, the C, and that creates something called the magic number, right? 12 times negative 45 is negative 540. Here's where the California method is not fun. You now have to find all of the factors of 540. And when these problems get harder, the numbers get bigger. You can imagine these will always be big magic numbers. So I'm not going to tell you the California method doesn't take a long time, but it takes the guesswork out. Now, some people just start like randomly trying to figure out what numbers go into 540. Don't do that. Start at 1 and work your way up. 1 times 540, 2 times 270, 3 times 180, 4 times 135. Okay. By the way, how did I know 4 went in? Well, 2 went in. If I double 2, right, I would have to take half of 270 to get the same answer. 270 is even. That's how I know that works. And you can do the same thing with 3s and 4s and so on. 5 times 108, 6 times 90. One of them is positive and one of them is negative, right? Because I'm multiplying to get a negative. I'm looking for the numbers that have a difference of 44. And it's not until I get all the way to the 8th set of factors, negative 10 and 54, that I finally get to a point where I'm like, oh yeah, the difference between negative 10 and 54 um, is 44. Now, because the middle term is positive, I'd want the bigger number to be the bigger number to be positive, the smaller number to be negative. Now that's not right because 12 times 12 is not 12 and 54 times 10 is not 45, but this is where you fix it, okay? This is called looking for the common factor and flushing it out. So what goes into 12 and 54? What goes into 12 and 54? 2 for sure, right? I can take a 2 out. I think that's it. I think I can just take a 2 out. So that would be, well, no, actually, I take that back. I can take a 3 out. So if 2 and 3 go in, I can actually take a 6 out. So I'm going to take a 6 out of 12 and a 6 out of 54. That's going to leave me with a 2x plus 9. Okay? I don't keep that 2. I throw it out. I'm going to write it over here just to remind you that we are taking it out because we're going to end up throwing it away. Okay? But we took a 6 out. Now look at the second set of binomial. 12 and 10, what goes into those? Well, this time it is just a 2, isn't it? Only a 2 goes into those numbers. So I'm going to take a 2 out, throw it away. What do I have left over? Well, a 6x minus 5. Okay. By the way, what is 6 times 2 here? 6 times 2 is 12. Do you remember what we put in extra at the beginning? We put in 2 12s, so one of those 12s was extra. So we just fixed that extra 12 right now. But look what's left over, and look how it works. 2x times 6x, 12x squared. Bam. 9 times negative 5, negative 45. But bam. And then here's the hardest part, right? Here's the hardest part. 2x times negative 5, 9 times 6x. That's 54x, okay, minus 10x, 44x. That's the part that would have been really hard to find guessing checking. So I'm not going to lie to you and tell you that this is an easy method, because this work right here that you have to do takes a little bit of time, but it does take the guesswork out of it. If you just follow the rules of this algorithm, it works every time. So now you know a method or a version of the California method, and you'll probably learn a slightly different way to organize the same ideas in Algebra 2 next year. But yeah, shoot me an email or a message if you have questions on any of this. Hopefully you only watched the parts you really needed to. If you did watch the entire the entire video, you spent an hour and 15 minutes of your life. I can't believe I just spent an hour and 15 minutes of my life, but there we are. Have a good whatever day it is, Friday, and good luck on your quiz. Adios. Ah, ah.